All right, hopefully you had a good vacation, just to get back into it, we'll pick up right where we left off, but we'll back up just a little bit to remind ourselves of what we were doing last time, since it's been over a week. We introduced a concept of binary search. Binary search is exponentially faster than the linear search that we began with because it exploits structure. The basic idea is that you assume that an array is sorted. And if that's sorted, then what you can do is you can look at the middle element. And if that's the thing that you're searching for, great, you're done. You got lucky and you found it at the very first place that you looked. Otherwise, if the thing that you're searching for, k, the key, is less than that, then because it is sorted, you know that it lies in the first half, the left half of the array. Otherwise, if k, the thing that you're searching for, is greater, then you need to only search in the right half. In either case, you've cut the array down in half each and every single time. So if you have 1,000,000 elements, then you cut it down into 500,000 elements with one comparison. You cut 500,000 elements into 250,000 elements with just two comparisons. ... And basically, you are able to get away with only a logarithmic number of comparisons, which is exponentially faster than linear search. To remind ourselves of what it looked like, here's our implementation. We're keeping track of a left index and a right index. We start the left index all the way to the left. We start the right index all the way to the right, right, at n-1. While these two have not yet met in the middle, right, then we're going to continue computing the middle index, relying on integer truncation to find the average, the guy right in the middle. And if that's the thing that we're searching for, then we're done. Here's your middle index. Otherwise, if the thing that we're searching for is less than that middle element, then we search in the left part by updating our right index to over here. Otherwise, if the thing that we're searching for is greater than the middle index, then we search in the right part by updating our left index over to the right section. Right? In either case, we've cut it in half each and every single time. We break out of this while loop when our two index values left and right have gone past each other, meaning that there's nothing left to search for, in which case we did not find the key and we return -1 here. Now, as we've said before, this is not rolling your own implementation of this is not the best practice. Instead, the best practice is to define these things called comparators, right? That take two generic void pointers and return something negative, positive, or 0, depending on the relative ordering of these. And then you use the built-in searching and sorting algorithms. So instead of using our own binary search here, let's use the standard libraries binary search. And to do that, I'm going to look since there are no man pages on the CS50 IDE, let's go ahead and look it up. It's called B search. What do you think the B stands for? Binary search. Yeah, this one's probably good enough. I'll zoom in on this. There we go. So there's B search. It is in the standard library. It's not in the search library because it is even more standard than that. It returns not an index value, but it returns a pointer upon a successful search. Upon a failed search, if it didn't find it, what do you think it returns? The only thing that it can return as a pointer that indicates something went wrong is null. It takes a key, which is a const void pointer, a generic key, so that it could point to an integer, it could point to a double, it could point to a string, it could point to a book. It takes an array, that's what this is, PTR to the array. It takes the number of things in that array. It takes the size of each thing, because remember, if we're going to make this generic, it has to know these 4 bytes are the first element, then these 4 bytes are the second element, these 4 bytes are the third element, ... right? Otherwise, if it's a double, then it would be these 8 bytes, these 8 bytes, these 8 bytes. If it's a book and it's 40 or 50 bytes, it needs to know how big each chunk is. Because if it's searching, it needs to say, this is the first element, or this is the second element, or this is the third element, right? And then finally, it takes that comparator as an argument. It's a function pointer, right? So let's come over here and not use our own binary search. Instead, let's use the built-in B search. Right? Now I'm going to go ahead and go back to this anytime we need it, but I need to capture that return value. So in this case, I am searching an array of integers. Let me go ahead and get rid of it. No, sorry, I do need it sorted. If it's not sorted, what's going to happen? Binary search isn't going to work because you can't exploit that structure. If you look in the middle and the thing that you're searching for is greater, say, I don't know, in the original here, I'm searching for 4, but I see 3 here. Where should 4 be? It should be in this half of the array, but it's not. It's over here. It's unsorted. Right? So there are going to be problems if I don't use a sorted version of this. We'll see that in here in a second. But otherwise, let's go ahead and search for the key k, it being 10 here. And I'll just say found. So it's an integer. Found is equal to a call to bsearch. Now, what do we pass into bsearch? I can zoom in on this if you need to up there. All right. The first thing that we're going to pass in is a key. Right? So, is that correct? Key is a regular old integer. What does it take? A pointer. So how do we take a regular old variable and turn it into a pointer? Ampersand. Good. The second thing that it takes is the array that you are searching. Is it going to be making changes to that array? Nope, it's just searching it. So it's going to be array. Right? What's the next thing? The number of things in that array. That's almost exactly like our binary search up here. We still have to pass in the array and the number of elements in it. Then the next argument is going to be the size of each element. So each one of these is an integer, right? So should it be 4 bytes? Yeah, that'll work, but is that how we do it? No. We don't want to hard code those values. Size of int. Because if I change this to a bsearch for doubles, I don't want to have to change that to 8. I'll just want to change it to size of double. And then finally, the comparator that you want to use to search. For that, I think we already made one, right? Called compare int. Right? And note that this is in increasing order, which is the exact same order that I hard-coded this to be. 1, 2, 3, 4, 5, 6, 7, 8, no 9, and then 10. So we'll pass that in. Now, if found is not equal to null, then that means it was a successful search. Printf found %d at memory location %p. And the line. I will dereference found and I will print out its memory location. Otherwise, if it's null, then I didn't find it. Printf did not find key value %d and the line key. Okay. Let's go ahead and compile this and see if it works. GCC demo. I think I'm still using book stuff in there, so book O and demo.c. There we go. So I'm searching for 10. Is it going to find it? Yeah, right there at whatever index value that is, but it's not by index anymore. It's, well, my version was index based. But the binary search bsearch version is going to be memory based. It found it at that memory location. Let's search for something else. What about let's search for an extreme element over on the left side, 2, and show that it found it at memory location blah blah blah. Right? Once again, if this were not sorted, would it be successful? Right? Let's find out. I'm going to search for 4. GCC, and let's run it. It did not find the key value 4. Well, yeah, you did. It's right there. Why didn't it find it? Because the way that binary search works is it starts in the middle. It says, oh, 3? Well, the thing I'm searching for, 4, is greater, therefore it belongs in this half of the list. And when it goes to try to search that right half of the list, does it find it? No. So consequently, we get garbage output here. I did not find it was index -1 for my version. Okay, so it needs to be sorted, and it needs to be sorted in the same ordering that the comparator that you're using is ordering it. If I change this to descending, in fact, let's do that. To do that, I'm going to go ahead and use a new comparator here. I'll call it descending instead. Okay. In fact, how could I get away with the fewest number of lines of code to do this? Well, if I just want to reverse it, what could I do? reverse greater than and less than, right? Oops. There we go. That'll work. Can you do it in fewer lines of code? You've already got the basic logic up here for an integer comparator, right? Why don't we call that? Int result is equal to that other guy, right? A, B. Now what are you going to do with that result? Remember to return something negative, positive, or 0 depending on the relative ordering. I want to flip that. So how would you flip that? If the result is negative, then I'll return something positive. Else, if the result is something positive, I'll return something negative. Else, return 0. Do I need all of that stuff? What am I doing? I'm taking something negative and turning it into positive. I'm taking something positive and turning it negative. I leave 0 alone. Is there an easier way of doing that? Times -1. So, -1 times that thing. Now, do I need to store that in a variable? No. I can just go ahead and return this. There, I've got it down to one line of code. So there's this thing called code golf, where if you get it down to the fewest number of lines of code, then the fewest number of characters of code, that actually still does it. So, can I do better? Do I actually need to multiply? Nope. Just negate whatever value you get back. Do I need to even do that? What do I do with A and B? I'm just flipping them, right? So B and A. There we go. I can't get any smaller than that. That's pretty much it. Right? If I'm going to reuse that other comparator up there. Okay. All right. So let me show you that if you use this comparator, then you're not going to get the correct results. This is indeed in ascending order, but if I use a comparator for descending, nothing will ever work. Let me go ahead and try 10. We knew that that worked before, but now it doesn't. Right? Did not find the key value 10. Why? Because it is sorted in ascending order, but you are searching for it under the assumption that it's in descending order, reversed. Right? So this comparator has to match the ordering that you're using up here. Otherwise, it's just B search. It's just like lfind that we showed before the break there. It is almost exactly the same arguments here. Okay. All right. Well, then that begs the question, right? How do we get it from an unsorted list or an unsorted array into a sorted one so that we can exploit binary search and use B search? Okay. How do we sort? For that, I'll ask you. As a human, how would you go about sorting those numbers that we just looked at? What would you do? Anybody? Got to start somewhere. So where would you start? All right, so the first one, right? 1. Should I move that anywhere? No. Okay. Why did you immediately gravitate to 1? You looked at all of them, and you were in the back of your mind. You were looking for what? The smallest one, right? So 1, find we call that the minimum, right? 2, place it at the front. Well, we already did that, right? But a computer can't just immediately look at all these numbers and say, oh, that's 1 and it's where it belongs. We saw that because our visual processing on a small scale, small input, is way faster than a computer, right? But now imagine doing this for 1 billion things, right? Are you going to go through 1 billion things searching for that smallest one? You're probably going to make a mistake along the way as a human. So how do we describe that to a computer? We have to start at the beginning and keep track of the smallest one that we've found so far. Then we'll look at 4, that's not smaller, not smaller, not smaller, not. And then finally we come to the conclusion that 1 is indeed the smallest number among these. And so we'll place it right there. Repeat. Now for the second one, do I look again at 1? No, it's where it needs to be. Leave it alone, right? It is sorted. Right? So instead, I'm going to look at all the remaining elements over here. And I'm going to find the smallest one. So, 1, find the smallest, minimum, right? And 2, place it not at the front, but at the second element, at index 1. Up here at the front, that meant index 0, right? So let's do that. 4, is that the smallest element? Well, that's the smallest element we've seen so far. Now here's my loop. 5, is that smaller? Nope. 2, is that smaller? Yep. So update the minimum element that you've seen so far on my hand over here. 3, is that smaller? Nope, 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 and nope. So finally, we found the smallest element over here, 2. Now what do we do with it? We place it at index 1. In other words, we take this element and we swap them. Right? So let's not fast forward, but let's redraw what we have so far. Black, there we go. All right. At this point, our array is 1, 2, 5, 4, because I swapped 2 and 4, 3, 7, 6, 8, and 10. There we go. Now, tell me about these two guys right here. They are sorted. Do not touch them anymore. This was my first iteration. This is my second iteration. What will my third iteration look like? Come on, copy. Let's move over here and paste. There we go. Got a copy of that. So here's my third iteration. Find the min among what elements? These. Among indices 2 through, and then the last one, n minus 1. Okay? Well, what is that going to be? So 5, that's my current minimum. I go through and I find the next 4, that's even smaller. Right? So the minimum so far is 4. Then 3, that we're getting even smaller here. 7, 6, 8, 10, we found the minimum. Right? It is 3. So let's circle that. And what do we end up doing? We end up swapping 5 and 3. Right? Dot, dot, dot. Let's think about this in an intermediate step. We'll think about this abstractly. Right? At some point, I have sorted elements 0 through, excuse me, I minus 1. Okay? I don't even know what they are. But this is sorted. Oops. Sorted. There we go. Now I'm looking at the ith element through the n minus 1th element. In other words, I'm on iteration I. Right? And I'm looking at these elements. And what I need to do, these are unsorted. I need to, 1, find the minimum among I up to n minus 1. Okay? Then 2, swap the minimum, and now think abstractly here. Where are you going to put it? So say I found it right here. Am I going to put it over here among all the sorted? No. Right? Am I going to put it over here? No. Where am I going to put that one minimum element that I found? Right at the front, and that index value was I. So swap min and I. Okay? Dot, dot, dot. Right? At the last iteration, what is it going to look like? So 0 through n minus 2, and then this is unsorted over here, n minus 1. I'm using 0 indexing just like we would in C. This is all sorted. Am I going to be moving this guy anywhere over here? Nope. Tell me about that guy. It's where it needs to be, right? It's at the end. Leave it alone. So this tells you I'm going to run I from 0, right, 0, 1, 2, 3, dot, 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 up to and including n minus 1. Or sorry, n minus 2. Right? You can run it to this guy, but guess what? It's one person. It is one number. What are you going to do with that one number? What's the minimum among one number? That number. So you end up swapping it with itself. Right? You can, I guess, if you want to, but don't do it. Right? So this all suggests a way of sorting. So let's come over here to a new sort demo. Okay. What I've done is I brought in stuff from Lab 7, where we generated a random integer array for you of a certain size. I read that size in from the command line, and then we print it out. So GCC sort demo. Oops, I need GCC utils.c, and that's it, I think. Sort demo.c. There we go. And then a.out 10. So it generates 10 random elements if I give it 10. If I do 5, it'll generate 5 elements. If I do 1 million, it'll generate 1 million, but I'm not going to do that. I don't want it printing out that stuff. Okay? But each time it is completely random. Right? So 10, 10, 10, 10. New values each and every single time. Right? Sometimes it's based on the timestamp, so I ran it too quickly, and it used the same seed there twice in a row. So let's go ahead and sort this. Sort the array. All right, so first of all, is that a good function name? Probably not. I'm going to call this what this is. Right? We introduced this idea of sorting because that's how humans would sort. They would go through, find the minimum one. Whether or not they knew it or not, they would be putting the minimum in the front each and every single time. They would rearrange these things. Right? This is called selection sort. Now, why is it called selection sort? Because you are selecting the minimum every single time and then placing it at the front. Going through the remainder and selecting the minimum there and putting it at the front. Okay? So we're going to sort this array, ARR and n, of size n. And we're going to have to write this now. So it's a void function. It's not going to do it's not going to return anything. Selection sort. It's going to take a const int star array. Is that correct? So const tells me that I'm not going to be making any changes to the array. Am I going to be making changes to the array? Oh, absolutely. I'm going to be rearranging it so that it's in order and it's sorted. So no, you can't put const in front of it. Right. So I'm going to codify this. There's going to be 2 loops. Once going through for each element right here, for I running from 0 up to n minus 2. And then what you're going to do in each iteration is you're going to find the minimum among I and n minus 1. Then you're going to swap the minimum and that I. Right? So let's write the outer for loop first. For int I equals 0, I is less than n, I plus plus. That would be the idiomatic for loop that you've always written. But I don't want to go all the way up to and including n minus 1, because that last guy is going to be there. If the first 5 are sorted, the last guy is already going to be where he needs to be. Right? So I'm going to stop short by 1. Right? Now I am going up to and including n minus 2, right? Because of less than or equal to. If I did less than or equal to, then I would need to adjust right there. Right? But I will go ahead and do it more idiomatic like that. Right? Now what I need to do is I need to find the minimum among elements ARR of I through ARR of n minus 1. That should be pretty easy for anybody to do, right? You've done stuff like this before in Lab 7 and Homework 7 or whatever it was, right? So I need another for loop. Actually, first of all, let me keep track of the min index. Int min index. Right. Where should I start that? For int, can I use I again? Not inside. So let's go with j. Why j? It's right after I. I, j, k, right? And then that tells you that if you are going to L, I, j, k, L, then they're doing something wrong. Because L should never be any variable name because it looks like 1, right? So I, j is start somewhere. J is less than something, j plus plus. Right? Now, if the jth element, ARR sub j, is less than what I've found so far, min index, then I've found something smaller. So what do? I update min index to be j. Right? Then after that for loop, I will swap the array sub min index and what? Array sub I. Just like we figured out over here. Swap the minimum and swap I. Okay? All right. So we'll come back to that. Let's start filling in these blanks here. Where should I start my min index? Again, think about this abstractly. At iteration I, you are looking from I up to n minus 1. So where do I start this entire process? At index I. So min index, I'll just say that it's I. Now, I could start this at I, but I would end up doing what? Comparing the ith element with itself. Why? Right? So I'll start at I plus 1 to avoid one more comparison. Right? Again, what I'm doing here is I'm assuming that this guy right here is my minimum, and then I will search the rest of this unsorted part of the array. Okay? What do I go up to and including now? I need to go all the way up to n minus 1, right? So n is what belongs there. There's your regular idiomatic for loop. Okay? Except that it starts somewhere different. Okay? Now, how do I swap two variables? 3 lines of code, simple enough. Int temp, go ahead and take out the min index, right? And then update the min index to the ith index, and array sub I gets the temporary variable. Right? I'm just swapping those. Okay? There. Let's see if it works. This is selection sort. Again, I'm going through, I'm selecting the minimum, and I'm putting it at the front. Going through, selecting the minimum, putting it in the front. Okay? So selection sort this and print it. Let's print it once before we sort it and once after we sort it so that we can see the change. 10 elements, there. 46, 25, it's completely unsorted there, but you tell me about this one right here. Is it sorted? Yep. And do we have all the same elements? Let's see, 97, that's indeed there. Just spot checking this. 40 and 40, 10 and 10. Looks like they're all there to me. All right. Suggestions on improvements. For example, this is a selection sort for what? For integers. What if I wanted it for doubles? Cut, paste, change. In fact, what would be the change? Int sort double, and this would be double. Right? What else would change? The temp. Okay. That's it. All right. Do it again for strings. What would change? Let's just look at and see what it looks like really quick. All right. So selection sort for strings. So it would be char star star. Right? There's the number of strings. Now, can I use this less than sign now? Nope. That would compare memory addresses. So what this is going to end up being is an strcmp between these two, and if that's less than 0, then you update the minimum index. And obviously, I would need to change this stuff down here. Right? Should I be doing this though? Copy paste, copy paste, copy paste. No. Right? In fact, should I even be using this dumb sorting algorithm at all? Let's find out. So I'm going to, first of all, let's make sure that it still compiles. Good. I want to increase the size here. What if I did this for 100? Right? I assure you that it is indeed sorted. Right? It is correct. Right? But now it's getting kind of unwieldy, so let's go ahead and trust it and not print it out anymore. Okay? So selection sort of 100 elements. Pretty quick. 1,000 elements. Still pretty quick. We're not even, on the human eye scale, we're still not seeing any difference here. 10,000. Right? You notice that was a little bit, right? Right. 100,000. Okay, did anybody time that in their head? That's all right. 5 seconds? Let's go ahead and time it. So if you did the full PDC module's time was a Unix utility that will time whatever process there is. And there's the real time. There's the user time. Why is the real time different from the user time? Your process is not always running. Sometimes the system is putting your process to sleep and doing other things, operating system things. And so the real time is here, and here's the actual user time, the actual time that your program actually spent running. So it was about 6 seconds. Okay? So going from, say, 10,000, which is 0.1 seconds, up to 6 seconds when I went to, what is that, 100,000? Yep. How many orders of magnitude is that? Remember, it's 0.1 seconds up to 0.6 seconds, 6.5 seconds. How much larger is that? 6.5 times? It would be if this is 1 second and then going up to 6 seconds. It's actually going to be 60 times, something like that, right? So let's choose a smaller number here. Let's just go with 20,000. Use that as our baseline. A quarter of a second. What if I doubled this to 40,000? Right? If it's like linear search, it should scale linearly as well. So if I double the input size here, I should have, if it's linear, it should only double the time. In other words, 0.5 seconds, but it doesn't. It's over a full second. In other words, it's 4 times as big. Let's see if that holds. Let's double it again to 80,000, right? So if it's 4 times as big, it should be about 4.4 seconds. 1, 2, 3, 4. Oh, really, really close. I think we're on to something here. It seems like when I double it, it doesn't go up double the time, right? If it was linear, it would look something like this. Oops. Right? It would look like this. N. In other words, linear. If I went from, say, 10 to 20, right, it would go from 10 to 20. 10 seconds, or whatever your time scale is, to 20 seconds, right? But it's not. It's going from 10 to 20. I'm going up to, from 10 seconds up to 40 seconds, which is way off the scale up here. Does that look linear to you? Nope. In fact, I'll tell you what it looks like. It looks like this. N squared. What do we call that? The quadratic, right? The polynomial. It's definitely not linear. Linear would be something like this, right? Something like that. Okay. But it is going to be quadratic. And we might go through the full analysis next time. But let's look and see theoretically, if I go from n to, say, 2n, in other words, I double the input size. What is the performance? Remember that I'm telling you that it is n squared. So if I plug in 2n for that, 2n squared, what do I get out of that? 4n squared. In other words, it is 4 times slower. Right? What if I go up by an order of magnitude? N to 10n. And again, it's going to be n squared. This goes up to 10n squared. Tell me how slow it is now. 100 times slower. Right? Because of that square factor. Again, let's come over here and do a baseline. What is it? 10,000. Let's go with 10,000. Right? That was roughly 0.1 seconds. So if I go up to 100,000, it's going to be 100 times slower. 0.1 times 100 is going to be what? 10 full seconds, right? Not exactly, but it's on the same scale there. What if I go up 100 more? That's 1 million elements. Is that big data, by the way? No. 1 million things. You should be getting that done in a matter of in a blink of an eye. But 100 times slower, what do you think it's going to be? If it took 7 seconds to do 100,000 and now it's 100 times slower, it's going to take over a full minute to do this. Right? I'll let that run. Right? Is there a better way? Qsort. First of all, doing it correctly is the better way. Right? I don't want the. I just want. Okay, there we go. Qsort. Well, first of all, I'll tell you what Q stands for. It stands for quick. Right? What we were just doing selection sort is slow. Right? It's agonizingly slow. But this all looks very, very familiar, or should at this point. You've got a base. In other words, you've got an array of generic things that you want to sort. How many items are in that array? How many bytes does each item take? And then finally, a comparator to use to sort it. Okay? So let's come back over here, and while that's running, let's go ahead and get rid of my selection sort here, restore these print values, and then let's go ahead and use Qsort. By the way, it doesn't return anything. Why? Well, just like our selection sort didn't return anything. It's going to take your array, rearrange it, and then return. Right? It is going to be making changes to your array because there's no const in front of this thing right here. Right? So the thing that we're sorting is ARR, the number of elements in it, and because it's generic, we need to tell it how many bytes each thing takes. And then finally, a comparator, CMP compare int. What is it? It's in demo actually. What was it called? I want both of these actually. Compare int and compare int descending. Right. I'll cut and paste and put those both in here. Has it been more than a minute? Oh, okay. It's even slower then. I wish I'd run that in the background. I could open up a new terminal, couldn't I? Split terminal? Yeah, there we go. I'll let you run over there, and we'll go ahead and recompile you over here. So GCC utils.c and sort demo.c. There we go. Oops. I'm in the wrong directory. There. All right. That one on the left is running still. All right. Let's go ahead and verify that Quicksort is actually working. All right. Is it? So there's the original array, all sorts of out of order. But Quicksort has done what? Has put it in order. All right. What if we wanted it in a different order, say in descending order? What would we do? Do we rewrite the entire algorithm? Nope. We just give it a different comparator. And now it's in descending order instead. Right? So let's go ahead and try this without printing it. GCC, there we go. A.out. It can do 10. It can do 100. It can do 1 million. 1, 2, 3. Over here it's still running. All right, so 1 million, blink of an eye. It is still running over here, so it's more than a minute. It's been way more than a minute at this point, I think. Right. So write your own algorithm, and really inefficient algorithm, or don't reinvent the wheel. Use what's given to you in the standard library and have it done quickly. Qsort, Quicksort. So which one are you going to do? I mean, in fact, you're just going to kill this outright there, right? It was more than 4 minutes already, right? So it was probably doing some thrashing because it was, well, a million's not that big. That's only 4 megabytes, right? So I don't know what the heck it was doing. Right? It's doing something really inefficient, but you get the idea. Over here, 1 million. I could probably go up to 10 million and start seeing a difference, a slight difference, but it's still going to be very, very quick, right? There's 10 million. There's 100 million. That's probably going to take maybe 10 seconds or so. In fact, let's go back in time. This first one, time. Give more room over here. There we go. Time. How big was that one? 1 million? No, that's 10 million. 10 million was only 2 seconds. I'm going to tell you that it's almost linear. It's what we call quasi-linear. And so it's going to be about 10 times as slow. So it'll be about 20 seconds. Let me show you what it looks like. So here's our graphs so far. We've got quadratic, n squared. This is going to be selection sort. Linear, just as a baseline here, is going to look something like this, n linear. There are no known linear sorting algorithms, by the way. In fact, you can prove that you can show mathematical proof that there are no linear sorting algorithms, comparison-based. Okay, but instead, quicksort, which is what we'll look at probably next time, is going to be something like this. All right, it's so slight that I don't think I'm going to be able to make it snap to it, but it's going to look something like this. It is n log n. All right. So instead of n times n, it's going to be n times log n. That other term is exponentially faster, just like binary search. Right? It goes from n, linear search, down to log n. That's why if you go from, say, n to 2n, and you've got n log n for your performance, this becomes 2n log 2n. All right? Help me out with the math there. What can I do with that thing right there? Think of this as A times B. What can you do with those logs? Split it. 2n times log of 2 log of n. How do you split it here? What goes there? You add it. Right? It's additive now. Tell me about this guy right here. Log base 2 of 2 is equal to what? Well, not 0. You can't get a 0 out of logs. 1. Right? This is equal to 2n 1 plus log n. Right? Which is equal to, I'm going to rearrange the terms, 2n log n plus 2n. Right? This one is the way more important term right here. Right? Why? Because it's n log n, and this one is just n. So, first of all, ignore this, right? And only focus on this one right here. How much bigger is it than this original term right here? It's about twice. Oops, that's a bit fat there. Twice as big. All right. Now, if you did the same exercise with 10 instead, like we're doing in the background right there, it's going to be 10 times as slow, plus an additive term. There, it's already done. What did I predict? That it would be 10 times slower. Before it was 2 seconds, and now it's only 20 seconds. Right? So what if I went up to, what is this going to be? A billion? How many zeros do I have there? Yep, there's a billion. You tell me, about how long would this take? 20 times 10 is going to be 200 seconds. 200 seconds is about what? 3 minutes, right? But let's ask Wolfram Alpha, what if we went with our dumb sorting algorithm, this selection sort algorithm right here, right? So we go from 1 billion. 1 billion is going to be 10 to the 9th, right? And that was, does anybody remember how big 10,000 was? I think it was 0.1 seconds. So 10,000, right? So it's going to be a factor of 100,000 times bigger. So 100,000 times bigger squared times 0.1 seconds. You tell me how long that'll take, Wolfram Alpha. There we go. Was I off by an order of magnitude? What was it?
I think it said something in days.
Oh, okay. Yeah, let's just go ahead and go with that. Oh, there we go. No, years is more expressive there. 31 years. Right? 31 years if I had used this versus 2 minutes, or what was it? 3 minutes. 3.5 minutes that we'll end up doing here. All right. So which one are you going to go with? Do the fancy one. Yeah. Exactly. So what?
Depends who I'm coding for.
Well, you get paid, sometimes you get paid by the number of lines of code that you write. but you never get paid by how long it takes your program. Trust me, I've never seen anybody do that. But if you can always put a delay. Sleep for. There we go. Now I can slow it down. All it does is just it does nothing. Right? There we go. Exactly. So, how does Q-sort or quicksort actually work? Right. So let's take that. Do I still have my paste here? Paste. Yep. There we go. There. I'll just use this as an example. It's a divide and conquer strategy, exactly like binary search. Right. What it does is it goes through and partitions it first of all. It says, okay, 1, that's small. I'm going to put it over here on the left. 2, or actually, sorry, I need a pivot element first. So let's go ahead and select what's called a pivot element, and I'll do that right here. All right. So this is going to end up being my pivot element. Actually, I shouldn't do that. Let me go ahead and upgrade that to something like another 7. There we go. Otherwise, it's not going to be interesting. Now what it's going to do is it's going to do a process called partition. It's going to put smaller elements to the left, and it'll put larger elements to the right. Now, larger, smaller is going to be relative with respect to this pivot element right here. So let's look at the rest of them. 2, that's smaller than 7, so it goes over here on the left. 5 is smaller than 7, so it goes here on the left. 4 is smaller, 3 is smaller. Then we get to 7, and so 7, 6, 8, and 10, they all go on the other side. Where does the pivot element go? Right here. Unfortunately, this is not a very interesting example. Right? Let me give another example here. I don't know, 5, 3, 10, 4, 7. I'm interleaving them to make it interesting. 1 and 8. All right. So here's my pivot element. All right. This is pivot. Why do we call it pivot? So basketball has started now, and you land. It takes step, or yeah, right. Once you stop dribbling, then you can step twice. Step, and then that becomes your pivot foot. You have to leave that foot down. You can pivot around it, but you can pick up your other foot, but you can't take. Otherwise, it's traveling, right? We all know this. There's this thing called basketball, right? All right, good. All right. So what are you doing? You're pivoting around that foot. We're going to be pivoting around this element. Right? The way that we're going to do that is by taking things that are smaller and putting them on the left side. Then we're going to take things that are bigger and put them over here on the right side. Right? 4, 3 was over there. 7 is greater than 5, so it comes over here. 1 is less than 5, so it goes over here. 8 is greater than 5, so it goes over here. Right? Then where does the pivot element go? It goes right in the center. Do we ever look at that pivot element ever again? Everything over here is less than the pivot element. Everything over here is greater than the pivot element. It's where it needs to be. It's sorted. Now what do we do? Yep, we continue and repeat the process on the left partition and the right partition. This is how it's done so quickly, right? I mean, look at that. Look at the right partition. It's almost sorted, right? In fact, when we select 8 here, 7 will go to the left, 10 stays on the right, and 8 ends up right in the middle where it needs to be. Do we need to go any further? Nope. What about this? 3 ends up being your pivot element. 4 will go to the right, 1 will go to the left, 3 ends up right in the middle. Right? This is how it gets done so quickly. Right? Of course, it's not perfect because it's highly affected by your choice of pivot element. That's why I said change this 1 to a 7, because what would end up happening if it was 1? Let's go back. What if that was 1? What about all these guys? They all end up on one side, which is really inefficient. It's no different than selection sort, right? So you can get unlucky with a bad break, right? But that's not going to happen in most cases. Is it done yet? Hey. All right. We said we predicted about 3.5 minutes, right? 210 seconds which would be 3 minutes 40 seconds, plus the time it takes to generate the array, we were almost dead on there with our estimate. Versus, what was the other estimate? 31 years, right? So when you go to lab tomorrow, right, you'll go through this process of doing the bad sorting algorithm, making it a little bit better by using comparators, making it more generic, and then finally you'll throw all that away and simply just use what's given to you, QSort and bsearch. Where is it? bsearch. Don't reinvent the wheel. You will never meet or exceed the performance of what's built in there already. All right. See you on Wednesday.